Hey kiddos, welcome back. This will be the last lecture on our Equilibrium chapter, and we're going to talk about something called solubility product equilibrium, or Ksp. And as I do that, I want to tell you a little bit of a secret, something I've been holding back on you since we've learned our solubility rules. It turns out that insoluble compounds are really not completely insoluble. Everything is at least a little bit soluble in water. Sometimes such a small amount of solid will dissolve in water that, for all practical purposes, we say it is insoluble in water. Let me give you an example. According to your solubility rules for bromides, let's see if we can remember that rule. It's the chloride, bromide, and iodide rule. It says essentially that they're all soluble except for silver, mercury, and lead. So we would say silver bromide is insoluble according to our solubility rules. However, it turns out that in a liter of water, this many moles, 7.08 times 10 to the negative 7th moles of silver bromide will dissolve at 25 degrees Celsius. That turns out to be 0.000133 grams, or I've converted that to ounces for you, will dissolve in a liter of water. Essentially, such a small amount dissolves, we say it's insoluble. Let me contrast that with something that, according to your solubility rules, is soluble. Potassium bromide is soluble according to your solubility rules. So if I put potassium bromide in water, a liter of water at 25 degrees Celsius, I can dissolve almost 70 grams. That's more than 500,000 times the amount of silver bromide that will dissolve in the same amount of water at the same temperature. So do you see why we say silver bromide soluble and silver bromide is insoluble and potassium bromide is soluble? Now, these ionic compounds will reach an equilibrium with their solvent, water, as they become saturated. And so we can write something called an equilibrium constant or expression for these solvation processes. We call these Ksps. This is an equilibrium constant, and it tells us how well a particular insoluble compound will dissolve in water. Let's take, for instance, silver chloride. All right, if we have silver chloride solid on the left, we have our equilibrium arrows here. It produces silver and chloride ions as it dissolves. Now the Ksp for this particular solvation process, as you would expect, is very, very small. After all, according to our solubility rules, silver chloride is insoluble. The Ksp for this is 1.78 times 10 to the negative 10th. So if we were to write the expression for this process, we'd have Ksp equals, and remember we put our products on top, Ag plus and Cl minus, and their coefficients become the exponents, but since there's no coefficient here, it's understood that it's 1, and so those are both raised to the first power, which we leave off of the expression. Now you might ask why silver chloride is not in my denominator. And that's a pretty good question, but think about it for a second. What do we leave out of equilibrium expressions? That's right, we leave out solids and liquids, and silver chloride is a solid. So it's not part of the equilibrium expression. That's in part why we call these Ksps. The Sp stands for solubility product constant. So we're just multiplying things together. Remember back in elementary school when they said summation is adding, difference is subtracting, quotients dividing, product is multiplying. So all we're doing is we're multiplying these guys together to get my Ksp. Now, what I'm going to do is I'm going to find out the molar solubility of silver chloride. Molar solubility is the moles of silver chloride, in this case, that will dissolve in a liter of water. And I can solve for that pretty easily. My equilibrium constant is 1.78 times 10 to the negative 10th. And wouldn't that equal, if I don't know the amount of silver or chloride ions produced at equilibrium, X and X? So, of course, that's equal to X squared. So we can solve for X, which would be the amount of silver or chloride ions, or the amount of silver chloride that actually dissolved per liter of solution. So it turns out all I need to do is take the square root of 1.78 times 10 to the negative 10th. And we end up with 1.33 times 10 to the negative 5th. And that would be the value of my X, which would also be the amount of silver chloride dissolved in a liter of solution. So let's see, what would that be in grams per liter? So 1.33 times 10 to the negative 5th moles of silver chloride will dissolve in a liter of solution. Let's see how many grams that would be per liter. So we'll put moles of AgCl on top, grams of AgCl, moles of AgCl on the bottom, grams of AgCl on top. And so we need to figure out the formula weight of silver chloride. So silver is 107.87 grams per mole, and chlorine is 35.45 grams per mole. So the formula weight is 143.32. So let's see what this would be. Grams of silver chloride per liter. We have 1.33 second EE to the negative 5th times 143.32, and we end up with 0.00191 grams of silver chloride will actually dissolve in a liter of water. That's about 2 milligrams of AgCl per liter. Now, that's all I really wanted to mention this year. Next year in AP Chem we'll talk a bit more about this, but I just wanted to make you aware about this sort of little secret that I've been holding back on you related to the insolubility of, or the solubility of what we call insoluble ionic compounds. Alrighty, hope that helps. Short video today, kiddos. See you soon. Bye-bye.